IUFRO is a global non-profit and non-governmental, not discriminatory organization that was established in 1892, and the headquarters is now in Vienna, Austria. What is important about such organization is the fact that it unites about 650 member organizations in more than 120 countries that represent all over more than 15,000 scientists. IUFRO is a sort of big umbrella that offers a global network for voluntary cooperation. And what is important to know is that such a network is open to all the individual and organization dedicated to forest and forest product research and related discipline. IUFRO also aims to contribute to achieving the Sustainable Development Goals set by the United Nations. You have the chance to join any of the 9 scientific divisions, over 50 research groups, more than 180 working parties, and 8 interdisciplinary task forces. So if you like, you can get in touch with any of almost 700 voluntary coordinators of this unit. So enjoy the webinar and have a good job. I leave the place to Angelo.
Okay, thank you, Professor Raffaele. So good day, everyone. My name is Ângelo. I am a PhD student of São Paulo State University in Brazil, and also head of forest technology at Asia Pulp and Paper, leading development and implementation of digitalization and mechanization projects. And today, I am very pleased to moderate the second session of this webinar, the second and last one. And I'd like to thank you once again for all of our great speakers for sharing their long and relevant contributions applying technology in the forestry. So regarding just a few words about digitalization, is a broad area. So, but it's still increasing business applications, which is combining sensors, apps powered by AI and so on. But in forestry, it goes from planning, operations, automation, quality control, forest monitoring, and etc. So it's a large and very broad area. So in this webinar, intends to bring just to bring a taste of very relevant applications, interesting work from our speakers. And now starting with the presentations, with no more comments. I'm honored to introduce a great professional, which I had the opportunity to work and learn a lot with, is Marcos Wichert. So Marcos Wichert is a Brazilian forest engineer with 25 years of experience in forestry industry in different parts of the world. He worked for most of his career in forest operations development, testing, and introducing new technology in the silviculture, harvesting, and logistics operations of forestry companies in Brazil, China, and Indonesia. He also worked for 5 years in forest management consulting companies in New Zealand, and now Marcos is working as the VP Plantation Forest Management for Stora Enso. He is based in Helsinki, Finland, but works giving technical support for the eucalyptus forest plantations in China, Uruguay, and Brazil. Welcome, Marcos. Please, the floor is yours.
Thank you, Angelo, for the introduction. Can you hear me well?
Mm-hmm.
And can you see the presentation, right?
Yep.
Okay. Greetings from Finland to you all. It's a pleasure to be here. Thanks for the invitation. And before we go for this specific digital wood trade project that I want to talk to you today, I need to give a little bit of a background where this project fits in our company and the challenges that we have here. So I work in Stora Enso. It's a Swedish-Finnish company that was a merge between Stora, that was a Swedish, it started as a copper mine in the past. It's quite old company, more than 700 years ago. We started with copper mining, and then Enso from Finland. And nowadays, the company really focuses on providing renewable materials to the world. And our aim is like everything that's made with fossil-based materials today can be made from a tree tomorrow. We are organizing 5 divisions. Our main products, they are focusing on replacing plastic in the food industry. So to be packaging related with the food industry, that's our main products. As you can see, we are mainly an European company, even though we have a global presence. Most of our production and sales, they are in Europe. I work in the forest division. So the forest division supplies the raw material for all the divisions. We are also leaders in providing wood products, timber for wood construction in Europe. As you know here, a lot of the construction houses and all that's with wood. So we are one of the major suppliers of wood for construction here as well. But we have some also eucalyptus joint ventures in South America, and also we have eucalyptus in China. And I work mainly with giving support for these eucalyptus plantations. But today we'll talk about a challenge that we have here in the Nordics related with our wood supply agreements. From the 2 million hectares of net planted forest that we manage globally, we have 10.4 million cubic meters of harvesting wood that we deliver to the mills every year. And that's only 27% of the wood supply that we need. And the main species here in the Nordics are pine and spruce. And then we have also a little bit of birch. That's our hardwood here in the Nordics for pulp production. We are, as other companies, and I think this is the other speakers who talk today about precision forestry, forestry 4.0, digital twin, etc. So Stora Enso also is in this journey to add more technology to manage our forests. That's such a valuable resource that we have. So trying to move from manual and reactive methods really for more like digitalized, data-driven precision forestry. So we are also in this journey. We started a project 2 years ago to map in all the forest units that we have, how was the status of the digitalization and precision forestry. And then first we map where each unit was, because at that time we had a lot of different tests and prototypes and proof of concept, and it was not integrated effort for the whole company related to this topic. So now we have an integrated effort that we call the Precision Forestry Program. It's a 5-year vision, so we already did 2 years. We have 3 more years to go, where we want to really have 100% digital data collection from the field. And that doesn't matter if it's with machines or if you still use manual operations. We want to have that data collected digitally in the field and sending that to a central database where we can get the different sources of data going to a central platform. And then from there, we can use optimizers, we can use artificial intelligence engines to help us to be more, to do more analytics, and that's supporting then the production units with their tasks and challenges. So I'm not going to talk about what we are doing in general with this, but I'll talk about one specific project related with this digital wood trade. So the first division, as I said, we supply the wood to the mills. So every year, the wood that we supply, for example, last year was 38.2 million cubic meters, and only 27% from our own forests. So the majority comes from more than 21,000 wood purchasing agreements we have here with private owners in Europe. And that's quite challenging. And here's a mature market. So the forest owners, they will sell that every year to different buyers. So it's difficult to have long-term wood supply agreements in this region. We really go to the market and then you buy. So you need to be very active to engage with forest owners, because you are competing with the other companies in the region that are buying wood as well. And here, the forest ownership, majority of the forest ownership, this is an example from Finland, but Sweden is similar. So you see that 61% of the forest is owned by private owners. And that's kind of a family business. So it's owned by families. The average size of a Finnish family forest property is around 30 hectares. And then the average age of the forest owners living in the rural areas is 60 years. And we have more than 920,000 forest owners in Finland and Sweden. So it's very important for us to have an accurate forest database, so we know the volume, the age, when it's approaching the time to do thinning, to do harvesting, so we can go there and negotiate with the forest owners and make agreements to buy their wood. And here in Sweden and in Finland, we have the benefit that the government gives us LiDAR information from the whole forest every 4 to 5 years, but it's a low resolution LiDAR. So if we get the total volume per hectare, it's accurate enough, But if you want the volume per log grade, and then as you saw there, we have 3 different species, birch, spruce, and pine. If you want to know the log grade by 3 species, it's more difficult, and that's not that accurate. So we need to invest now more in using drone imagery, combining a lot of different sources of information. So the LiDAR that we get from the government, we fly our own LiDAR with higher resolution, we fly with drones, and then we need to, and also satellite image. We combine all that to then improve our models about the knowledge of the forest. That's the volume by log rate, that's the more important one, because we can optimize the value when we know the volume by log rate, not only the total volume. So how we did these deals in the past. So usually what happens is we have foresters from our company living in the rural areas. They know the owners, they talk to them, and in the past, we had these kind of foresters living there for 20, 30 years. So working most of their careers in the same place. So they have the knowledge of the region. So when a thinning happens, they have been there. So they remember next time they go there for the harvesting, clear cut, that what happened in the past. So when they look the results from the database showing the volume, they can see, oh, there is a mistake here. This is not accurate. And then because based on their experience, they correct that problem there. Nowadays, that's changing. So 2 things are changing here and making more difficult to work the way that we used to work. First, the forest owners now, they are moving to towns. So when these guys, they retired or they die, that forest goes to their kids. Their kids are living in big towns in Europe. They are not there in the rural areas anymore. And our foresters now, they are young. The old ones are retiring. They only stay 2-3 years. So it's a high turnover. So we don't have that knowledge from the past with them anymore. And then we need to evolve. So in 2021, we start to look to our processes that most of things today, you can do everything digitally, right? You can buy clothes digitally, you do banking digitally, but we kind of sell and buy wood the same way. So in 2021, we started this digital wood trade program to really, and then that was, first we did a market research with the private owners. We need to kind of, how can we develop tools that we really integrate all the informations and sources of informations that we have. One thing that's very important, as I said, is the log grade, volume by log grade information. So we have one cadastre system that needs to be updated frequently to be very accurate related with the volume by log grade. Because what happens is that nowadays, when we do the contract, and then we say there, what's the volume by log rate? And of course, the most valuable logs are the ones going to the sawmills. When we do the clear cut, if the information that we sign a contract with the forest owner is not that accurate, when we finish the clear cut, we need to go back to him and say, look, unfortunately, we got more pulp logs than saw logs. So you'll get less money in your pocket. And that's not good. So we need to kind of have more accurate information here in this cadastre, so we can then do things remotely. So we don't need the foresters to go to the forest all the time because that information is already in our system. And then from there, they can develop, know the volume by log rate. So what we are doing is kind of focusing on integrating the different sources of information we have, being more accurate about the data cadastre that we have. And then also we are now preparing one, and then I will go a little bit deeper in detail now. That's a kind of a digital customer relationship that we are developing here. And that's our vision for the future. We are not there yet, but we want to have this going live by the end of next year. And what we have at the moment, we have in a website. So it's the forest owner can go there, click, and they can offer or ask us that, okay, can you come here and visit me to check? I would like to sell my wood, or can do digitally. That's already a platform that we have online that's working. This is one example of the Finnish website. But this is kind of not still, it is digital, but it's the engagement, it's more like the traditional way that, or you call the forest owner, or the forest owners need to click there. what we want to, and it's kind of the website, so it's not an app for the phone. What we are doing now is transforming all this to an app application. And this is just one example about how we want to really have this fully digital experience with our customers that are the forest owners. So this is just one hypothetical example about where we want to be in the near future. So try to imagine that this is Anna. She's a private forest owner in her 40s, and she lives in a big city, and she got this forest from her family. She doesn't know much about forests, and she haven't been there for a while, but then we know that forest. And then through, we contact her and say, you can please download this application. And then we tell her that we can start to negotiate, because it's time now to do a thinning, or we are in the rare area here, and do you want to discuss with us? So we approach her through the app, and then she starts to have some options there, what she wants to do, and what kind of a knowledge level she has related with wood trade deals. And then what's important for her as well. So we start to check there, okay, what do you want? Earnings in a short term, or you want a kind of a long-term forest management there? You want to have like social sustainability is important for you or not? How about environmental sustainability? So she will give us feedback, what's important to her, that will help us to prepare and customize an offer. And then she will be able to see the comparison there of the different options related with every year, what will be value coming out of thinning, what will be the cash flow she will receive, and what's kind of a CO2 emission reductions as well. So in the future, we want to bring the carbon there as well. We are working to try to bring this biodiversity and carbon perspective as well to the platform. And then she will see there the property, what's the tree, how many trees we are planning to harvest. And then after everything is done, she signs the contract there with us. Then we will tell her, okay, now it's time we are planning to start harvesting there by this date. And then you get the deposit in your bank by this time. And even in the future, we could have like cameras in the machines, and she can click there and see that, yes, the machines are there, machines are working, or some drone footage about what is the operation, or after we finish the operation, she can see what's the status of the forest there. So basically here it's a different approach. So we are solving two problems here with this approach. One, as I said, we have high turnover in our forests, and then they don't have that knowledge on the ground, what happened in the past. So with more accurate information in our cadastre, in our systems, that it's okay. We don't need a person that knows the whole history there. And also the new forest owners, the new generations, they are not living in the rural areas anymore. For them, it's not that important to have the face-to-face signed contract and talking to us in the field, because they are living in big towns in Europe, Helsinki or other places. So for them, it's more like really the digital customer relationship. And this application, it's appealing to them that, okay, this makes sense to them because they are used to do everything using apps. So why not to also manage their forest and the engagement with the buyer through the app? And doing this, we try to, of course, position ourselves, Stora Enso, in the region as a kind of a good partner to them, so they can perhaps start to consider doing long-term agreement with us for wood supply in the future. So that's the project that I would like to share with you today. Time is short, but that's just some highlights about the challenge that we have here. It's our perspective from the Nordics, a little bit different from other parts of the world. But anyway, this is one project that we'd like to share with you all. Thank you for the invitation again. I'm open for questions, and if not time, you can also email me later on. Thanks.
Thanks so much, Marcus. Great presentation and excellent example where we can apply digitalization from knowing all the forest measurement, all the data collected from forestry technical point of view, but also this relation with business and the end customers and actually the suppliers. A very good example. Let me check. I think we don't have any question in the chat, but just to inform everyone once again, feel free to put in the chat, and maybe we can keep moving on. And then if you have any question, Marcus, I think he's still with us and can reply later. Okay, great. Thank you. So moving to the second presentation now, I would like to introduce John Arlinger. John Arlinger has 25 years of experience working primarily with issues related to standardization of forest machine data, information systems related to forest machines, analysis of wood raw material for industrial use, and software development. Most of the work is closely related to the global de facto standard for forest machine data, standard for D 2010. That is maintained and developed by Skogsforsk in close cooperation with many other partners, such as most of the major manufacturers of forestry machines. So thank you, John. The floor is yours. I think you're in mute. Yeah.
Okay. The sound is clear now?
Yes.
Yeah, good. Thank you, Angelo. It's definitely a pleasure to be here today, even though quite a bit of an awful pleasure. Compressing 20 years of work into 20 minutes, that's a little bit tricky. Anyway, I'll try to do a quite brief and quick overview of the Stanford standard, and then primarily with a focus on the more modern version that we call Stanford 2010. It's Stanford, that's an abbreviation for Standard for Forest Machine Data. It's what I usually describe as a global open de facto standard used by the major manufacturers. And it's administrated and primarily supported by Skogsforsk and financed jointly by a large number of different machine manufacturers. We also work in very close cooperation with our Skogforsk sister organization Metsitaho in Finland. It's to be a data standard quite old, from the mid-80s, when the first optimization softwares were introduced in harvesters. And we have 2 open meetings annually that anyone that is interested can participate in. All official documents, all the main documents are available at the Skogforsk website. So that's where you can find XML schemas and a number of different documentations about the standard. A little bit of a historical background and how the standard has been used, and then primarily from a Swedish perspective. The standard came about in the late 80s, and when introduced, the focus was primarily on how to control the bucking or the value optimization in a standardized way, and also getting the different software systems in the machines to behave in similar ways. In Finland, the production data was taken into use quite early on in the 90s, while in Sweden it took a number of years before focus moved into how to use and use harvested production data on a large scale. A few years later, focus moved on towards getting production data, etc., from the forwarder. We had a lot of work on improving the measuring accuracy and the building a quality certification system where the Stanford standard was heavily included, operational monitoring and GIS information. I would say that the last decade, and I think this will continue, focus has to a large extent been on how to integrate and how to use the Stanford data together with other types of data and using it for new purposes, for example, for the forest industry or forest owner perspective. And of course, globalization has been a very strong driving force as well. Around 10 years ago, we started to use the new version, that what we call Stanford 2010 version, taking it into practical use. And this is something that is quite, the newer, more modern format is definitely helping us when trying to use the data in more advanced ways. Yeah. The standard is now with Stanford 2010. It's an XML-based standard with quite a high degree of flexibility. A basic idea that we've tried to follow is that we try to register and report what we actually measure, rather than to report different calculated key figures. We have worked on now have a much better way of administrating the standard with clear rules for how to update and modify the standard in comparison to the first decade's work. And it is constructed in order to make it simple to store the data in a database. For example, having the possibility to have globally unique identities down to each individual logs to make certain that you never risk working with duplicate data. A little brief overview of different types of messages included in the standard. We have instruction files for each specific type of machine. Up until recently, only working with cut-to-length harvesters and forwarders, but as you will see later on, now extending into new machine types as well. But the idea here with the instructions is to be able to change, for example, optimization parameters in a flexible way, make it possibly easy and simple and quick for the operators to implement new updates of products or adding new products, avoiding having the operator to do a lot of manual work. An important aspect has also been to try to avoid any type of machine dialects, which we used to have a fair amount of. Geographical information is also possible to send in a Stanford format, and this means that to update a whole fleet of harvesters based on shifting markets demand is now done within a couple of hours, comparing with the old standard version, where it was more like changing the direction of an oil tanker. It could take quite a number of weeks before you got your whole fleet updated. Another important set of standard messages is the production data. Again, we report what we measure with a high frequency, and the machines can nowadays do this in more or less automatically. This means that the fact that we report what we measure, we have data on each log, so we can reconstruct the trees. And we have information about the trees and the logs and can calculate whatever key figures we are looking for. We can also reconstruct the forest and use this type of information, for example, as a reference data for training LiDAR models, updating forest inventories, doing follow-ups or monitoring of thinning operations, etc. A third area is operational monitoring. Again, we try to keep as high resolution as possible, meaning that we report individual activities, and with those activities we can connect, for example, how much volumes have been harvested, the fuel consumption, etc. Making it possible to, for example, draw this type of timelines describing exactly what activities a machine has been carrying out during a day, and with detailed information about each individual activity, such as production, fuel, driven distance, or reasons for different downtimes, making it possible to, for example, model fuel consumption for a logging team or study productivity. As I mentioned, up until a couple of years ago, this was only a standard for cut-to-length machines, but that is not the case anymore. We have, during the last year, also added the possibility to report production, for example, from fellow bunchers, skidders, and yarders. And we actually now have a couple of controllers that has implemented the Stanford standard for fellow bunchers, but not for skidders and yarders, as far as I know. But this is typical. You add something to the standard, and when whether or when the standard is really implemented in a machine, it's usually dependent on the market requirement, whether there is a demand on the market for it. So you typically don't really know how long time horizon will be before you see practical implementation. But fellow buncher exists today. Today, focus so far only on logging operations, but with an increasing global interest in mechanized scarification and planting, we have started work on covering also these types of different machines, where the idea is to make it possible to report geographical information describing both machine movements. This already exists for harvesters and forwarders and fellow bunchers, but will be included in the case of regeneration work. But then on top of it, geographical information describing the treated points or lines that has been planted and or scarified. But this is still under discussion and development. Probably at least another year before we have finalized this work. So where are we heading? What are the main trends from my perspective? One very important trend is the fact that we want to combine the machine data, the Stanford data, with other types of data sources. And this is partly one of the reasons driving another very important trend, and that is trying to improve the positioning of machine movements, logs, and stems. We have the possibility to record tracking information, machine movements during harvesting and forwarding. We have for quite some time now registered on a large scale the position of the machine when felling trees, but we now see systems starting to generate also high quality positioning data on where the tree was actually standing with the felling. And we have now upgraded the standard to make it possible in the near future to also include information where the log is located, as well as upgraded the standard to make it possible to record positioning data where the forwarder has been picking up and unloading logs, getting both data on where the logs were located and where the machine was positioned. When starting to use the standard Stanford data, there are usually a number of stumbling blocks that are definitely worthwhile to be aware of. To be able to use the data in an efficient way, you have to know that the measuring system, especially in the harvester, is working well. You have to have calibration control. You have to have operators with certain levels of skills and acceptance. You have to have communication solutions, which are usually not much of a problem in Finland and Sweden, but a very important issue on most other markets. Keeping the softwares updated, finding dealers that have the right competence, the right knowledge about the software systems is quite often a little bit of a problem. Final slide. Stanford standard can, from my perspective at least, provide us with very large amount of detailed data from real work conditions, which has its pros and its cons, but at a very low cost. Thank you very much.
Thank you so much, John. Great. Thank you, not just for the presentation, but all of your contributions. So I think everyone that knows harvesting machines already heard about Stanford D, knows the importance, and not just to monitor the machines, but to increase productivity and the cost efficiency of this operation. So it's very, very important, even having some difficulties to implement, as you pointed recently in the last slide, in the previous slide. It's not just a matter of technology, but a process, a complete process combined. And I also thank you, and especially because you helped a lot when we had to implement a large-scale fleet in Brazil, and you could help us very closely, and we were able to succeed that implementation. So we have one question here from the chat, John, is from Danny Boy Ciboa. He asked, "Hi, John. With Stanford D 2010, can we still put STM files from the machine? Does the data also need to be decrypted? Will it be easily be read on Excel, or will it have to be converted?"
The old standard version is it's never decrypted. The standard doesn't include any decryption. Of course, someone else can decrypt or encrypt it. Sorry. The old standard, an STM file, for example, it's an ASCII text file that you need a specific parser to read the data. While the newer, more modern XML format, the HPR file, you can use any XML parsers to parse. It's much simpler. Was there some other question? No. Did I answer it?
I think so, John. If it has any more details needed, you can explore by the chat.
Yep.
I think also there was a question here a comment here from Eric Jenner, wondering if it be exploring like standard for mechanized reforesting for planting. But I noticed that you already present that is also in the timeline to be developed. Yeah.
Yeah, it is.
Just let me double check here. Yeah. I think that's all. There's one last question from the same person, Danny Boy. What is the recommended calibration frequency to improve machine data and pulpwood operation? I think that's interesting. Important one.
Don't calibrate too often. I think that's a bigger problem that it's not possible to say exactly how often to calibrate, but it is more often a problem that operators calibrate too often and you with too little data, and usually the guys that has, or the machines, the harvesters with good measuring, they do not, they try to keep their the hardware up to date and check it frequently, but they usually don't need to calibrate very often. Maybe a couple of times a year, not more than that. But this also, it's based on my Swedish experience.
Okay. Okay. Thank you, John. I think that's all, John. We will keep moving, and then there will be some additional questions in the chat if you stay with us and could help with that. Thank you so much, John. Before we move to the next presentation, I would like to invite Giannini to give an announcement.
Thank you very much, Angelo. So Angelo and I, we would also like to use the opportunity to make you aware that there's a special issue in the International Journal of Forest Engineering. I just put the link into the chat, and the special issue is about digitalization of forest operations. And to make it short, the core question addressed in the special issue is how digital automation and IT-based applications can be used and made applicable to benefit the wood supply chain. And there are a couple of bullet points which manuscripts would be in the scope of the journal, and we warmly invite you to check the link. And if you want, you can contact us anytime if you have questions, and the deadline for submission is by the end of August. So feel free to have a look into this special issue. Thank you.
Okay, thank you, Janine. Now moving to the third presentation. It's about Forestry 5.0 and digital twin. We would like to introduce Michele Balasso. She's a forest professional with a breadth of experience in the forest supply chain, integrating knowledge from forest management to wood production. She's currently leading the digital transformation program of Forest Training in 141, Australia, incrementing the precision and fidelity of data capturing for better forest operations and improved decision making. So, Michele, please, the floor is yours.
Thank you, Angelo. And thank you, Raffaele, for inviting me to present today. And thank you to all attending. It's great, actually, to present to such a great audience this somewhat heard of, but not very well-known topic of forest twinning. As Angelo said, I'm Michele Balasso. I'm a forest scientist, and currently I'm employed in 141 as a manager of the Digital Twin program. 141 is a company in South Australia and New Zealand, forest growers and softwood processors. In this webinar, I'll share my research contribution, and this presentation does not reflect the views, operations, or objectives of 141. Today, I'll dive into Forestry 4.0 innovations with a focus on forest twinning. The topic is rather large in nature, but I'll bring it closer to forestry with some specific examples and some use cases, as well as touching on the challenges ahead for digital twin implementation into the industry. Many of us probably hear weekly about or are already working into Industry 4.0. However, there is still a bit of confusion around what it actually consists of. The Industry 4.0 term encapsulates a new generation of industry where the physical and virtual worlds are to be integrated for smarter and more sustainable management of industries and societies. Daringly, it is the merging of the real with the virtual to harness the strengths of both while tackling some of those weaknesses. There are several concepts, components, and technologies characterizing Industry 4.0, and some of which might be more heard of and others less. You will start hearing more, for example, of cyber-physical systems, which are integrations of computation, networking, and physical processes, which form a network where physical entities and virtual entities monitor and control one another, acting in an embedded system. Common examples that we currently find are the smart grid, autonomous vehicles, industrial control systems. Well, then we have the Internet of Things, which we hear on the mouth of many people. However, it's not as hard. It's just simply the network in which cyber-physical systems interact, acting as a common platform for sensors, devices, and humans equipped with sensing and communication technology. Other buzzwords of Industry 4.0 concept are the positioning and identification technology, sensor technology, machine-to-machine communication, and human-to-machine communication. And then we have big data, cloud computing, so on and so forth. These concepts gave the rise to the digital twin as an IoT-based cyber-physical system. Now, if I haven't confused your ideas yet, I'll move on to see how these concepts act out in the context of forestry, which is deemed to become Forestry 4.0. The overarching question here is if and how the forestry sector is in shape to move towards Forestry 4.0. So far, when we think about digitalization in forestry, we look at single technologies supporting the forestry sector with innovative ways to do forest management, harvesting, transplantation, milling, and so on. But that's not quite enough. To truly move towards Forestry 4.0, we need an holistic view where there is an end-to-end digitalization of the physical assets of the supply chain, which can operate in a virtual environment through integration and interconnectedness. The single technologies are important because they are enablers. However, to be actually useful at their best potential, they need to be integrated into new business models, which are based on analytics and appropriate and pertinent decision support systems. There is a very large amount of data generated by these technologies, which needs to be handled through modern methods, enabling big data analytics through, for example, cloud computing, machine learning, and artificial intelligence. This in turn requires an appropriate network infrastructure, which enables high-performing technologies. We need advanced connectivities for real-time data acquisition, and there is also a need for a scalable, centralized, and shared computing platform for storing, integrating, and managing all the information acquired. This seems a lot because in fact it is, and it's an effort that can be taken only collectively. To truly reach Forestry 4.0, a new paradigm of connectedness is needed, where entities in the supply chain need to be willing to be collaborative, transparent, and coordinated to achieve new levels of industry cooperation along the supply chain. This is the space where digital twins can and will make a contribution. Now that we've seen upon which basis digital twins emerged and can be utilized, it pays to dive into some definitions and characteristics of the digital twin, which is in essence a virtual representation of a physical object, a system or a process, which is synchronized at a certain frequency with reality and represents reality at an acceptable level of fidelity. We can use digital twins for a variety of applications fundamental in Industry 4.0, as simulation, optimization, AI analytics, prediction, information sharing, and smart production systems. The definition is important as it touches on the fundamental components of a digital twin. We first have a real entity or a series of entities to twin into a virtual environment. The physical entity is a real-world artifact. It can be a vehicle, can be a tree, a system, or even a model of a system. And the virtual entity is the computer-generated representation of this physical artifact. The two are connected by types of data, information, and processes, which are transferred between the entities. The data which is being transferred are the parameters that we use to define the digital twin, and the fidelity is a concept encompassing the number of parameters transferred, the accuracy, and their level of abstraction. We can have ultra-realistic or high-fidelity parameters, or we can have parameters more at the macro level. So we have a real entity, we have a virtual one, we have a series of parameters passed between the two, which are to be accurate and abstract enough for the digital twin to exist. The physical to virtual connections allow the state of the physical entity to be transferred and realized in the virtual environment, meaning updating the virtual parameters so that they reflect the current state of the real entity. This happens through a metrology phase, which consists in capturing the relevant information about the real entity, and a realization stage where the virtual twin is updated with the data captured from reality. Obviously, the opposite can happen as well when there is a virtual to physical connection, which takes place when the digital twin contains some functionality that needs to be realized to change in a physical state. For example, in a process control, machine parameters, or production management. The act of synchronizing the virtual with the physical is called twinning and is an act of measurement and realization. We can call two systems twinned when they are in complete synchronicity with one another. And then it derives that there is a twinning rate, which is the frequency at which this twinning occurs, and it needs to be paced for the use of the digital twin. This leads us to a very important aspect of the digital twin, which is their use. We find two main categories of digital twins, passive and active. Most industries need active digital twins, but they end up building passive ones as the funds run out or for a lack of appropriate design of the digital twin solution prior to its implementation. As the terms say, passive digital twins are not to act out in reality. They are most images of a real entity for storing information and for data repository. Active digital twins are a little bit more exciting. They are being used for decision-making and operational tasks. And we find many types that pertain to one of the two topologies. Digital twins can be imaginary when the real product doesn't exist yet. So they're used to build the product for design and to test out before building the actual entity to send to customer. But instead, for digital twins of real entities, we have monitoring digital twins, which are used for description and diagnostics. And then we have prescriptive digital twins, which are projection of future states, behaviors, or physical entities using predictive analytics, forecasting and simulation, and machine learning methods. The predictive digital twins can become prescriptive, in which intelligence is added for recommending corrective or preemptive actions of real-life objects. We then have autonomous digital twins, which, as the words say, operate autonomously and fully control the behavior of real-life objects without the intervention of humans. Lastly, we have more passive digital twins, which are recollection. They are used to maintain a complete history of the physical object, which may not exist longer in the real life. If it's a tree has been harvested, if it's a product that is being disposed of, it keeps the memory of the product. When it comes to digital twin for forestry, the simple image that forms into the mind is that of a virtual forest, which is mirroring the real one. However, that is only one component of a digital twin. But what about the others? How are they to be understood and applied in the forestry space? As always, this really depends. What are we mirroring? In which virtual reproduction are we creating it? Which parameters do we need to consider? These and other questions are those to answer for creating a digital twin. But there is one more that underpins all of them, and it is, for what do we need a digital twin? What is our use case? We've seen that many types of digital twin exist for digital purposes, and we should define which is the specific type of types that we need for our research, commercial, social, or environmental use case prior embarking on the journey of creating one. This is directly followed by specifying the characteristics that we've seen previously to obtain as much clarity as possible on the final details. And then we can move towards a prototyping stage in which we try out the ideas before going to full implementation. This seems quite silly, but actually this process allows any organization to understand what the requirements are prior to launching themselves into the effort of looking into digital twins. For forestry, there are many use cases for digital twins, as there are forest processes to emulate or to ameliorate. The most heard of is the case of a virtual forest, which could improve forest inventory with collection of data at the scale of the single tree, revolutionizing the classic stand-based management that has characterized forestry for centuries. A full integration of forest inventory data, harvesting and hauling information allows then for almost a full picture of the supply chain, with enough information to simulate different harvesting options, plan operations based on simulated results, optimize decision-making at the tactical operational level, but also control operation in real time through the digital twin of the supply chain. Other examples that are possible with the build of a digital twin of the forest are fast simulation, biodiversity hazard management, reconciliation of harvested versus predicted yield, forecasting, modeling, and prediction. And diving more specifically on the characteristics of digital twin for forestry, Again, it's important to define which is the real entity that we're trying to twin. For example, we can consider a forest stand as a collection of trees, or the single trees composing the final stand, through which we can study the interactions of the single trees with the environment or with one another to plan out silvicultural treatments. Or rather than trees, we can focus more on the production side, twinning how the machines influence wood production and the forest life cycle, as for site preparation, site treatment, silvicultural activities. And diving even deeper into the production facility, we can think about twinning a production line where timber is processed from logs to final panels and then transported to the customers. Defining the real entity to be twinned is a fundamental step, as it will dramatically change the way in which the virtual entity will look like in the virtual environment. Single trees can be reproduced as point features in a GIS environment or as 3D models if captured with aerial imagery or laser scans. Machinery and production lines will require CAD models, while production facilities will require BIM type of modeling, and transportation requires different types of virtual models. The parameters that we're looking at when we look at forest twinning vary enormously, depending again on the use case that we may be looking to gather information on. Virtual forests for forest inventory may be restricted to only 3 variables for measurement for forest inventory, while a virtual forest for ecosystem management may require also environmental data, climatic data, or other type of biodiversity information. Other parameters that may be relevant are those regarding harvesting activities or wood production systems, as the harvesting, transportation, and final milling. You can see how variable these data types may be and how complex the development of a digital twin for a full supply chain is. Moreover, we also need to look at other challenges, which are the synchronization rate. How many times do we collect data on our forest or on our processes or on the production systems? How do we respond to changes? For example, during wildfires, harvesting, production stops for maintenance. And finally, how is the history of the data collected throughout the life cycle of a forest or throughout the production activities handled and stored for future use? Another aspect that we need to consider is how the metrology happens. If we need still manual measurements, or if we use technologies as remote sensing, as satellites, laser scanners, UAVs, terrestrial scanners, or other sensors. Other technologies that can aid the measurements can be tracking systems for timber, harvested production data, hauling information to log quality data from the scanners at the mill. And then looking at the realization component, we may need systems where humans interact with the machines, which are the most common ones, which could happen in reality or in the virtual reality environment or through an augmented reality technology, or then machine-to-machine interactions, moving them more towards autonomous vehicles and autonomous operations. We then can pull all of this together in a framework with real forest, machinery, and mills on one side of the picture, which are measured with sensors transmitting information to the virtual entity, where this data realizes the state of the virtual entity through database and cloud computing, thanks to an appropriate network and communication technology. In the virtual space, then we have the tools to aid the decision-making, as a simulation, prediction, analytics, which inform potential future states to be measured and then realized into the actual forest or production line or sawmill through actuators, humans, or machines. What this framework suggests is circularity, which needs to be at the forefront of any organization building a digital twin, because it is in the continuous exchange of information between the real entity and the virtual one that operations can be facilitated. There are nonetheless some challenges to get to the full realization of digital twins for the industry. There are inevitably high implementation costs that are connected with technologies as cloud computing, resources connectivity, upgrading of the network infrastructure, and also having reliable and robust equipment to do all the measurements and the sensing. Another recent challenge is also cybersecurity, which can become even bigger when we store all our information in the cloud. On the data front, we do have issues in representations of the data, and as John told to us some minutes ago about the data standards. For example, data exchange formats that might not be compatible to be exchanged between different pieces of machinery and technological resources. So we have a data integration problem. We have also concerns of data redundancy, meaning that the same data is collected at different parts in the supply chain, and sometimes it is not even similar. Latency of data can be a concern when it comes to the synchronization of the real with the virtual, as there can be quite a gap in between data collection and receipt and final use. Lifecycle management of data needs to be properly managed to preserve the necessary information and to make a good use of it. And then the ownership of this data and the sharing of information are especially hard ones when we want to consider the full integration in the supply chain. Less heard of, we have challenges from the societal and environmental points of view. We have changes in the work organization. We need skilled people that are able to deal with complex information systems. And currently there is a gap in our industry, which is very concerning already, but is going to be even more concerning while we move towards Forestry 4.0. Then we also have stakeholder fragmentation, which is not new at all into forestry, but is also connected to a lack of trust and little willingness to cooperate in a supply chain, mostly due to privacy and competitiveness concerns. And last but not least, we should consider the energy management issue, as the large amount of data that is collected from any production system can generate a lot of information that needs to be stored, managed, and utilized, and can get off hand quite quickly. I hope that this presentation has provided you with an overview of Forestry 4.0 and the digital twins, but also has challenged some thinking and provided some ideas for the future of our industry. Thank you all for listening, and please feel free to contact me for further information or to stay in touch on the social platforms.
Thank you so much, Michele, for your excellent presentation and for highlighting us how it's a complex thing, and it's the future. So not every disruptive technology is challenging and takes some time to be applied. But as the industry already moving in that direction, probably forest is to go quite quickly on that as well. But as you already greatly highlighted, it's a complex thing. It's not easy, but in the same way, it will be a great opportunity also. Thank you so much. We have one question here in the chat before we move. Is Dr. Vikas Paul Singh asked, these technologies are very effective, but have also need skill and may have high costs. So are these digitalization applications feasible in poor countries which have enough forest cover?
In case of poor countries, we can look at data that is freely available. For example, when I'm thinking about remote sensing, there are satellite platforms that derive data at a good resolution for forest inventory, for biodiversity management and fire management. When we look at forest inventory under canopy, then we need better data, which may require platforms that are more expensive. So we will need a higher effort from forest organizations to apply into poor countries. I saw a comment previously that mentioned a potential to implement forestry carbon projects that will finance these forest projects in poor countries. And I think that could be a great option for countries that can't afford network and communication technologies. Also, with having data in the cloud now, it's much more easy to handle because you don't need a physical space where data is put into a server in a specific country. So there are opportunities for facilitating this, but there is a need for a conscious effort to make it real.
Okay, great. Thank you so much, Michelle. So we'll move, and then if there are more questions, we can continue by the web chat.
Thank you.
Okay, thank you. So now, the last but not least, I'd like to welcome Mauricio once again. Thank you, Mauricio, for your time and your transition in a very late night in Chile. So I would like to introduce Mauricio that will give us a presentation about wood supply chain automation, solutions, opportunities, and challenges. So Mauricio Acuna has been recently appointed as research professor in automation and AI in forest operations at LUC, Finland's Natural Research Center. He's also an adjunct professor in forest operations at the University of Sunshine Coast, Australia. He has over 28 years of professional experience in forest and supply chain management and has developed solutions for national and international private companies, universities, and research organizations. His research interests include sensor technologies and artificial intelligence forest operations, mathematical programming, and optimization techniques for forest management and operations, wood and biomass harvesting and transport logistics, operations research, and decision support systems, also harvesting machines evaluation. Dr. Acuna has served as Deputy Coordinator of IUFRO's Division 3, Harvesting and Transportation Engineering, and has been an active Cost Action Force Energy program member. He is also a member of the editorial board of the following journals: Forest, International Journal of Forest Engineering, Croatian Journal of Forest Engineering, Annals of Forest Research, and Ames Energy. So thank you, Mauricio. Feel free start your presentation. And the floor is yours.
Yeah, thanks a lot, Angelo, for this kind of introduction. Can you hear me well?
Yes.
Yeah,
I can see your
excellent.
screen. Also,
Yeah. Okay, excellent. And so today I'm gonna talk a little bit about automation, AI, and optimization for operations. More from a research and educational point of view, and also I'm gonna talk a little bit about some solutions, some of the things we've been doing in Australia. Also, I'm gonna talk about the opportunities and challenges of using this sort of technology and in forestry. And
Mauricio, sorry to
sorry.
interrupt you. Can you put in full screen?
Yeah, let me a second. Window. Can you see the screen now?
Not yet.
Not yet.
No, it's loading. It's loading.
It's loading. Okay, good.
Yeah. It's here, but not in full screen.
Yeah. Okay.
I guess you can go for slideshow option.
Okay, so that means. Oh yeah, now I'm gonna. What about now? Can you see
Great,
now?
perfect. Thank you.
Okay, yeah, thanks for that. And so as Angelo say, I'm now transitioning my job from research fellow in Australia to a professor in AI and automation in Finland. And as I said before, I'm going to present this topic from mostly from a research and educational point of view, talking about the solution, opportunities, and challenges of automation, AI, and optimization. Just the first slide to put all these things in context, and I'm not going into the details of everything here in this slide, but basically just tell you that at the moment, in 2050 will be 10 billion people. The demand for wood as per current rate would be 6 billion cubic meters, and that means basically that we will need around 100 million hectares of new plantation to meet the demand, and that basically has several implications. One is that we will have to increase the current harvest capacity 4 times. Also, many organizations and companies basically are going to start harvesting and doing operation in very marginal areas, and we are going to have an increase of thinnings, harvesting subsoil and steep terrain. So that's why many organizations in the world are actually looking for new technologies, to be more competitive and efficient. And also, we don't have to forget that we are competing with other industries, such as plastic or steel frame industry. But also, we are competing in forestry with other regions in the world. So there are different wood baskets in the world, and we are competing on costs. And here we have one slide on the left that show you basically a comparison between different regions and how efficient or cost competitive are this region. And we can see that most of the low costs are found in the southern hemisphere, especially in Chile and Brazil. And this is very important for some parts of the world because we have to be competitive. And again, as I said, they are looking for technologies and including optimization, AI, and automation to be more competitive and efficient. And so why we are actually, or why the organizations are adopting these sort of technologies? The first thing is because they want to face labor issues. In many regions in the world, it's becoming very, very hard to attract people, to attract workers to work in the forest. And the use of automation and AI could help with that, to make the forest operation work more attractive to people, but also to increase safety. And I think operation could be more safe if we can implement this sort of technologies. Those are the social aspects. But also, and as I said before, organizations want to continue increasing productivity and efficiency. Mechanization was a big boost like 40 years ago, but now the use of mechanization in conjunction with AI and automation also could make a boost and continue increasing productivity and efficiency in forest operations. Also, there is an interest in reducing the environmental impact of forest operations, and many companies and machine manufacturers are working on technology to actually reduce the footprint of the machines and reduce the environmental impacts on soil, especially on water. In the end, so organizations are using this technology to have more sustainable wood supply chain. And so here on the right, you have a few examples of some systems being proposed in New Zealand. The one on the right, top right, a robotic log sorting facility, and also working on unmanned vehicles and that sort of equipment. Also, there is a value chain opportunity here. I borrowed this slide from Professor Glenn Murphy. So you can see here from at the very bottom, we have forest emergency systems. So as Michelle and others have mentioned here, they are working on developing, and provide better forest inventory systems and that can provide information about the wood quality and quantity. And Marcus also talked about that it's important to have inventory at the log product level. So we need to know exactly what sort of product we can harvest from our forest. And we have the improved stand records, management system, and the AIS. In the middle, we have organizations that are using optimization for optimizing stands to log markets, because we need to we have a set of markets and we have to provide those products to the markets. Optimal backing in the middle, so very important decisions when we are cutting the forest, because we want to maximize the revenue, we want to maximize the income for the organization, for the landowners, and it's very important to extract the most valuable product from the forest. And then we have other aspects, logistics and transport optimization system, and then improve process manufacturing as well. But as Michelle mentioned, also there are some challenges for the adoption of optimization, automation, and AI. So, and here we have just a few examples. This is not by no means a comprehensive list, but the first one is to identify the right business process to automate. I think we need to fight with something that is easy to implement, and we have to identify which processes can make most impact when we adopt this sort of technology. Also, we have some. We need to make sure that we can integrate, and we are providing compatible system with the current systems, with the legacy systems, and that's not always an easy task, because we have an old system in place and new technology and new system that we want to implement. So they have to be a transition, and in many cases, those systems has to be compatible. Again, we are managing a large volume of data, and with all the implications that has, and we have to have systems in place to manage that volume of data. We need to identify how we are going to extract information from the data we are collecting from different sources, and in the end, many organizations actually have issues to implement other systems because they cannot actually manage the data that is going to be used as an input for other systems. Also, we want to maintain security and privacy. That's a quite critical aspect when we are managing data and collecting data from different sources. In many cases, we are lacking of skilled labor, so we need to prepare and train the people who are going to use those sort of technologies. And this is also valid for educational systems. So how, as researchers, as professors, we are providing our students with the cutting edge technology, and how we are training and educating people, and our students, how we are preparing those students for the future. That's not it's not a trivial sort of task. In many cases, organizations have a lack of budget to invest in automation. Some of the changes are quite expensive, and difficult to implement. There is a lack of time for continuous improvement. Change management there. And also, as the other speaker mentioned, there is a cost and time involved for the implementation. So all of these are some of the issues that are, or challenges that organization will find when trying to implement this sort of technologies. And here, and again, other speakers had mentioned some of the technological pillars that basically shape the Industry 4.0. And we have cloud computing and mobile technologies that are pretty much used in the forest now, especially in the Nordic countries. Machine to machine, machine communicating to other machines, making decisions in real time, 3D printing, advanced robotics. Again, a lot of work at the moment underway in Canada and in the Nordic countries. Big data analytics, Internet of Things, tracking and tracing technologies like RFID and other technologies, and cognitive computing. Here, just a picture to basically show you some of the pillars, technological pillars in forestry. Forestry 4.0, a term that was coined by, I think, several years ago by FP Innovation. But here you can see some of the technological pillars in forestry. So collecting data from different forest sources with different sensors and sensing technology, unmanned vehicles, and LiDAR sensors and drones and that sort of technology. Also developing remote control systems and manned vehicles and satellite imagery, communicating machine with other machines in the forest, and in order to make better decisions. Here you have some of the most important technologies at the moment that several organizations, especially in the Northern Hemisphere, are working to provide this technology. And here we have an example of, because we've been talking about analytics and how we can use the data we are collecting for different purposes. We have, and again, this is something Michelle showed in her presentation, that basically there are different types of analytics. And here, the only thing that I want to emphasize that is prescriptive analytics, the one at the top, that basically can optimize or provide a course of action when we are optimizing systems. The three previous ones are quite common in forestry. So we want to provide data. We are collecting data. We are simulating data to make forecasts. We want to know how our trees grow. But in the end, when we want to optimize the system, it's particularly analytics that's the job. And here you can see on the right that this sort of analytics is considered to be at the cutting edge of data science and often referred as the final frontier of business analytics. And here we have an example of wood supply chain optimization. And I'm not going to explain everything here in this picture, just to show you and to let you know that there are so many decisions that we have to make when we are actually cutting a forest and delivering the different products to different customers. And for example, how we can allocate different machinery to different forests, what sort of product we are going to cut, what sort of tracking systems and track configuration, when we are going to do the chipping in the forest or at the mill, etc., where we are going to install our facilities, etc. But in the end, the forest logistics has a goal, and this is produce the right product at the right time and deliver this product to the right customer with the goal of maximizing revenue. And this is some of the examples that have been implemented in Australia. So I have developed some software and decision-making sort of tools. And again, this is just a picture. I'm not going to explain everything in detail here, but on the left, we have a fast plan, which is a tactical planning tool. So basically, it's a spatial tool where you can optimize the time of the harvest of different crops in the forest, but also we can optimize when to do the roading, when to do the road maintenance, and also we can add some environmental constraints such as green-out constraint, or we want to maximize, for example, control the maximum opening area. We can implement and test those sort of green constraint in a tactical tool. The outputs of that tool are input for the next tool, which is MC Plan. It's more an operational sort of tool. We can organize the transport and the harvest operations. I've been using MC Plan to optimize harvesting and transport operations in situations where companies are drying logs or drying biomass. So the tool also can optimize the drying times in the forest before doing the transport, because drying logs and biomass in the forest can reduce transport costs quite substantially. And then the output of that tool go to a truck scheduling system called Fast Track, a tool that I developed possibly 7 or 8 years ago. So imagine you have a fleet of truck and you need to optimize the routing, the scaling, and that tool in a few minutes can provide with a near optimal solution. And in the last years, also been working with some dispatching companies like Trimble or Asset in New Zealand, trying to develop real-time dispatching systems. So these are an example of optimization solutions. And before COVID, or around 2018, I started working with AI and machine learning, deep learning in forest operations. And as again, Michelle and the other speakers showed, and it's been used for different purposes for forest inventory. In my case, the interest in basically in two areas: forest inventory and forest operations. And here, for example, you have one example on the top right. It's a system developed by Ponsi in Finland, released last year, which basically has a sensor on the harvesting machine and can detect, trees in real time and provide and assist the operator for him to make better decisions about which trees to be removed during the thinning operations. Yeah, so this is we're going to see this sort of technology more frequently in the future. So sensors working on harvesting equipment, and here more examples. In the middle we have remotely controlled machines already working in New Zealand. So you have a lady controlling the machine on a steep terrain using joysticks and that sort of technology. Virtual and augmented reality at the bottom, unmanned vehicles on the right. And also there is another technology that hasn't been mentioned yet, but it's blockchain. So blockchain is a transactional system, and it's a distributed sort of ledger system where we can record transactions use an encryption system, so it's quite protected, and so different stakeholders can have access to those transactions. And in forestry, there are not many case studies at the moment. In other industry, we find much more examples. And but one application in forestry could be to trace products. For example, I know there is some organization in New Zealand exporting product to China and using blockchain technology to actually do the tracing, because we know exactly where the tree was cut, and who did the harvesting, the transport, and yeah, we can trace all the history of that product in the supply chain. Also, a few years ago, I started working on volumetric measurements. I've been working on this topic for around 7-8 years, and I started with a drone, before COVID, and we did our first trial with a drone, capturing picture, creating a 3D model, and from there we were able to actually measure the gross volume. Just a few years ago, we've been able to develop a fully automated system to measure volumes, so from logging trucks or from log piles. And on the left and bottom, you can see a use of deep learning. So from point cloud data, we have an intelligence system. So we train the model with different truck loads, and now we are able to detect the loads. So the green part of the picture that you can see in that image, and we are able also to apply a volumetric algorithm to actually calculate the volume. Also, if we are able to see the faces of log, we can develop, or we can use another sort of deep learning models, the one that you see on the right. And with one of my PhDs, we developed the first deep learning model that can detect log faces, and we also can use that sort of approach to measure volume. This is my current project in Australia. So we try to install some sensors on harvesting equipment. The picture in the middle actually comes from Scandinavia and from China. Like 10 years ago, they started with the project installing sensors, quite expensive sort of LiDAR sensor and harvesting equipment. And on the right is the system that Ponsi developed and released last year. So you can see the LiDAR sensor. That's an Auster sensor on the harvesting equipment, and now they are providing that data in real time to the operator during thinning operations. And we've been trying to do the same, how we can collect data in real time with the sensor, what sort of data we can collect, because it's a very challenging environment. And at the moment, we are working with two companies, commercial company outside in France, and also Auster and Acuna in the United States. On top of that, I've been working with some organizations in Europe to try to develop a tool called Forest Vision, in which we can capture data, point cloud data with different sensors, And in the tool, we are going to provide several algorithms, one to detect the trees, one to actually estimate diameters and height, detect all the trees in the landscape, measure the crown size, and also we are going to add a module, an optimal bagging module, so you can see on the top, on the bottom left, right. And we are testing different methods to actually estimate diameters, because well, in most of the research, people use they fit circles, but we are also testing other approaches to estimate diameters. Yeah, so that's the tool. So it's going to be a visualization tool, but also it would have different modules where the user could, you know, the tool provide different metrics, different sort of data to and information to the users. Also, because we are mounting sensor and harvesting equipment, we are also testing other approaches to actually do the detection. And here you have an example of semantic segmentation from 2D images. We can use a LiDAR sensor for that purpose, or we can use what is called depth cameras. And at the moment, we are training a model. This is eucalyptus in Tasmania. And in Sweden, there's also already a commercial company called Catan that developed a similar system, the one on the right. So with a camera or a mobile phone, you can actually detect trees and estimate diameters. In our case, the main purpose is to use that in a harvesting equipment and to do detections in real time. Also, as part of my research, I've been testing most low-cost sensors. You know, and here we have some examples of the low-cost sensor we've been in testing. I purchased a LiDAR sensor, but it was very, very low cost, like 5,000 or 7,000 Australian dollars. And also we've been testing depth and stereo cameras, you can see on the left. And then there is a range of depth and stereo cameras, interior real scene, the Z1, the OT. And also we've been also validated some of the data using the LiDAR, because LiDAR also has a LiDAR sensor. And so yeah, the main use of the iPad in our case has been to validate the measurement of the data collected with other more sophisticated set of sensors. And yes, so just to finish, and also I'm being working with other people and different training and learning materials. At the moment, we are with other 25 experts or experts in logistics. We are writing a book on wood supply chain management, and there will be one chapter just devoted to the use of this sort of technology, you know, AI, automation, and most of the technology that I have presented today. And I expect to publish that book and in spring in next year. Also, I am developing courses for students, for undergrad and grad students. 3 different courses: one on optimization with Python, one on point cloud data processing with Python. So always using open source sort of algorithms and libraries and tools. And the last one that I'm preparing at the moment is a course on artificial intelligence, pretty much focused on object classification, detection, and segmentation in forestry, also using Python. Okay, so that's it. Thank you very much, and hope you have enjoyed the presentation. Thank you.
Thank you so much, Mauricio. Thank you for your time and for bringing so many applications and different technologies and sharing your experience and how is this scenario of all these technologies and analytics involvement. And just a final comment here, and before just let me check. We have two questions here, Mauricio, before we give the final comments. It's Janine asked about if there's anyone knows about training data freely available, if there's any platform, website that could be used.
Yes, so training data for developing a deep learning model for object detection, or what sort of, or for the machine learning model, or?
Yeah, for the detection. So
for
identification of tree species or other labels, yeah.
Yes, so I have good data sets, but obviously because it was captured as part of my project with private companies and forest growers in Australia, I would have to know if I can share that sort of data with other users. But yeah, I can check.
Okay, thank you. Another question from Mr. Ario is this AI implementation suitable for African countries, considering several factors?
Yeah, I suppose Yeah, so everything that I showed today could be applicable in any condition. And as I emphasized in my presentation, I'll be using low cost sort of sensor. That was part of my research. I'm not using very expensive sensor here. Some of the dead cameras or sensor cost less than $1,000, and I've been using open source libraries, Python. You know, you can do basically a lot of things at a very low cost. Obviously, you want to implement that at a commercial operational level. Obviously, that increase the cost, but yeah, so we can do something in in any condition.
Okay, great.
Mhm.
Thanks so much, Mauricio, once again.
Mhm.
And just closing comments here, we checked, as we mentioned at the beginning, this is a quite broad subject, but also a lot of opportunities for forest business. So we see that from data collection, integration, analysis crossing different data sources is something that we are moving in that direction. Also, technology needs to be cost efficient. We see that as, for example, in Stanford E, maybe in the past, people thought that would be quite difficult, but right now is a reality. And just bringing more and more sensors like cameras, LiDAR is becoming more cheaper and more feasible, as you mentioned, Mauricio. So that's seems to us that our sector is already really moving towards these kind of technologies and implementation. So we cannot forget that we need to have like not forget the process and people involved, and also it should be cost efficient in the business applications, like a good example that Marcus has shared with us. So as professionals, we need to be aware of that and be prepared to this new reality. So the future is already ongoing. Yeah. So that's my perception. I think that's not only of all the things that we discussed today, but many other examples. If you keep in mind, everything will be related, is similar to these current discussions. So thank you, everyone. We will close this session and hope we could see everyone soon.